Okay, so let's take a look at another sample problem. It says a solenoid has an inductance of 53 millihenry and a resistance 0.37 ohms. If the solenoid is connected to a battery, how long will the current take to reach half of its final equilibrium value? Okay, so just now we know the time constant is like L over R. Actually, when t equals tau L, it is not halfway to the equilibrium point. It is something like 60 point something percent, around 64%. Okay, so let's see. But at the very beginning, we can just simply calculate the tau L first. So we have tau L equals L over R, which is 53 times 10 to minus 3, and then over 0.37, which is 143.2 millisecond. Okay, so we have the equation like I equals E over R, and then 1 minus exponential to negative t over tau L. So actually we don't really know what is E, and we know R, we don't know E. But actually this value is not really important because it asks you how long it will take to reach half of its high final equilibrium, which means that at the very beginning, when t equals 0, e to the 0 is 1, so 1 minus 1 is 0, which means that I, when t equals 0, is nothing but 0. And when t equals infinity or tends to infinity, I infinity is like E over R. So when it means reach half of its final equilibrium, which means that this factor is 0.5, then we don't really care what is E. So as much as this term is 0.5, this is what we would like to find. So which means that we should have a 1 minus exponential to t over tau L equals 0.5. Okay, so we just move this over. So we will have exponential to negative t over tau L equals 0.5, because 1 minus 0.5 is 0.5. Okay, so let's take log on both sides. Or maybe we can just take the reciprocal on both sides. So we have exponential to t over tau L equals 0.5. Equals 2. So if we take the reciprocal, so this negative sign changes to plus sign, and then on the right side we have 1 over 0.5, which is 2. Okay, so and then we take log on both sides, lateral log on both sides. So this lateral log as exponential will cancel each other. So we have t over tau L equals lateral log of 2, or it means that t equals lateral log of 2 times tau L. So which means that it is 143.2 millisecond times lateral log of 2. So this is like 0.1 second. Like this. So this is not really difficult, as much as you know what is so-called half of its final equilibrium point, or sometimes I will call it the steady state.稳态这个也是平衡值嘛。Okay. So no question, I'll just move on. So next we will talk about the energy stored in a magnetic field. So in chapter 25 we already know what is the energy stored in an electric field. So at that time UE if you still remember, UE is 1/2 CV squared. 1/2 CV squared. Now it is 1/2 Li squared. So just now we have V equals LD IDT, which is this one, and actually P equals IV. This one always hold. Other format like P equals I square R or equals V square over R. These two only work for resistor, but for capacitor or inductor, yeah, we should go back to this P equals I times V, and P is something like the derivative of the energy. And then here we have V equals LD IDT, which is what I have mentioned in the last hour. So we have I LD IDT, and then we try to integrate it over time, something like this. So the total energy is like integrating this one, and then from 0 to UB, and then UB is this expression, and then we have dt and dt cancel each other. So we have ILDI, so this is this expression. So this is another derivative. So previously I let you know is we try to change E to B, and then we try to change epsilon naught to 1 over mu naught, and then also like the electric dipole moment or the magnetic dipole moment, you can also try to change them, then you can get the duality. Here it is also the same case. This is the energy stored in the E field, this is the energy stored in the B field, and then V and I, the voltage and the current are also the duality variable, and then also C for the electric field, and then L for the B field. And then so here it means that you try to change C with L and then V with I, and then you will also get the duality between this one and this one. And here it also it derives this later. So before going to the energy density, we have another sample bubble first. So here it says a solenoid has an inductor and a resistor. If a 12-volt EMF is applied across the coil, how much energy is stored in the magnetic field after the current has built up its equilibrium value? So in that case, so first we can try to calculate I equals E over R. So because the circuit is something like, this is the battery, this is the resistor, this is the inductor. And as I mentioned, for this circuit, when E is a constant, and then when T tends to infinity, the inductor is somehow like a short circuit. So when T tends to infinity, it is something like this. This is out, and this is short circuit. Okay, something like this. So the current is nothing but I equals E over R. So which is 12 over this 0.35, which is 34.38. Okay, so now we can just use the equation. UB equals 1/2 of L I squared. And then we can plug in the value. 1/2 times this is 53 times 10 to minus third power, and then times 34.3 squared, which is 31 joule. Okay, so this is pretty simple. And then for the next one, after how many times constant will have this equilibrium energy be stored in the magnetic field? So we also face this keyword half, but it is a little bit different from the previous case, because now we would like to have half of the equilibrium energy rather than half of the equilibrium current. So, and as you can see, UB equals 1/2 of Li squared. L doesn't change, a half of course doesn't change. So the only variable changing is I. So if we would like to have half of the UB, which means that the I should be I over square root of 2 rather than I over 2. So we would like to have this I. So in that case, we should have I half should be 1 over square root of 2I rather than 1/2 of I, because we would like to have half of the equilibrium energy. And here we have a square here there. So if we just have a 1/2 I half, which has a factor of 1 over square root of 2, and then take the square, it becomes half of the UB. Okay, so in that case, we can have 1 over square root of 2 equals 1 minus exponential to negative T half over tau L. So similarly, we can just move this over. So we have exponential to T, exponential to negative T half over tau L equals 1 minus square root of 2, which is like square root of 2 minus 1 all over square root of 2. And then we can have a T half, which is tau L times lateral log of square root of 2 all over 2, square root of 2 minus 1. Okay, so I just jump over a step. If we take the reciprocal of the left side, it becomes positive. And then we take the reciprocal of the right side, so it becomes a square root of 2 over square root of 2 minus 1. And then we try to take lateral log on both sides, so the lateral log and exponential will cancel each other. So we have a T half over tau L, and then on the right side we have a lateral log of this one. And then we just multiply tau L on both sides, so we have a T half equals tau L times lateral log of these terms. Okay, so this is nothing but 176 millisecond. 176 millisecond. Or actually, this factor is actually 1.23 times. 1.23 times, because actually it does not ask you what is the time. It asks you how many time constant. So which means that T half is like 1.23 tau L. So this is how many time constant, which is 1.23. Okay. So next, we talk about the energy density. Just like what we have done in chapter 25 for the energy density in the electric field. So at that time, if you still remember, UE is 1/2 epsilon naught and then E squared. So just as what I mentioned, you just change E epsilon naught to 1 over mu naught. So mu naught is here in the denominator. And then change E to B. So then you can change this equation to this one. Okay, so but how we can verify it, this is not a strict proof. It only verify it with an inductor. So yeah, of course, rigorous proof is quite difficult. You may try to find it on the internet, but yeah, it's not very important to know the rigorous proof. So we just try to verify that this is true for an inductor. So here, similarly, we have UB equals capital UB over the volume. So this is the energy stored in the B field, and then divide for the volume. Volume is A is the cross-section area. This is the length of the inductor. Okay, so UB is 1/2 of Li squared. So this 2 and then this Li squared. This is UB, which is Li squared over 2. Okay, and then we have L over capital L over small l. You put it in the front, and then I squared over 2a. So we just reordering it without changing anything. Okay, so previously we have capital L over L equals this one. We just derived it previously. And then we also have B equals mu 0 In. We derived it in the chapter 29. So we try to put this one here. So this L, capital L over L here, and also I. So this one will become I equals B over mu 0 N, and then we put it to here. So here for the first term, L over L is this one, which is actually this one, and then here I square is this term quantity square, which is here, and then over 2a is here. Then we can see that we can cancel some of the terms. A and A can be cancelled, and then here we have n square, and n square can be cancelled. Also we can, here we have mu 0, and then we have mu 0 square in the denominator. So finally we have mu 0 here, we have 2 here, and then we have b squared in the numerator. So this is what we would like to have. So this is the density of the energy density of the B field. So in chapter 33, when we talk about the EM wave, in chapter 33, yeah, we will make use of this one to see in the EM wave there are energy stored in the E field and also energy stored in the B field. So yeah, so light is a sort of EM wave, and later on you know what it really means, hopefully. Yeah. So next we talk about the final phenomenon called the mutual inductance. In Chinese, it is called 互感应. So just now we already introduced the self-induction, 自感应. Now we have mutual inductance. So which means that if we try to put two inductor close, and then there will be something called mutual inductance. Of course, you may have heard another term called a transformer. 变压器. Not the 变形金刚. Yes, transformer. Also not the transformer in the AI. We have also new transformer in the AI for the natural language processing. But here, the transformer means the 变压器. Maybe you should have learned about that. Just like this one is just like this one is a inductor. Is a transformer. Okay, so so we try to put two inductors close to each other. So here it means that so here we have two individual circuits, but we try to put it close together. Of course, they are a little bit different. So for the left one, of course we have an inductor, or we have a coils, and then it is connected with a battery and a tunable resistor, so that just as what I've mentioned, it can generate some current going through this inductor, and then of course it will generate some B field. just as what it indicates using the green arrow. Okay, so as much as it generates the B field, and if this B field is changing, then the magnetic flux density of the other coil, so there will be magnetic flux changing. It will generate some induced EMF, induced current. So for the second coil, it is closed, but without any other battery or any other EMF. This one only indicates that this is an ammeter. This is only an ammeter to see whether there is any current going through this coil. Okay, so in that case, if this current is changing, which means that the B field is also changing, so that this magnetic flux is also changing over the second coil, then there will be some current. Okay, so just now we have EL equals negative L di dt, which is for self-induction. Here we will have a similar equation. So we only write it as E2 because this is the EMF induced in the second inductor or the second coil, and this is I1, which is the I in the first coil. Okay, so this is the I in the second coil, and then it generates the EMF for the second coil. So we use the subscript 1 and 2 here. And of course, yeah, we have to take the derivative. And then rather than using L for the inductance, we use M, which means the mutual inductance. The M means mutual inductance. Mutual inductance. 互感值. Inductance means is 电感值 in Chinese. So mutual inductance is called 互感值. Okay, so this is analogy to the self-inductance, but here we call it mutual inductance because if we have some current for the second coil, it will transfer some power to the second coil to generate some current there. And then for this one, actually the coil doesn't change, but we try to change the battery and the resistor to the second coil, and then we move the ammeter to the first coil. So here we try to generate some current I2 going through the second coil, and then of course it will also generate the B field, and then if this I is changing, then this magnetic flux over the first coil is also changing, then it will generate induced EMF and induced current. So here we have I2 here, there we have I1, we have I2 here, and then there's E2 is E1. So yeah, so this is actually the same coils, but here we try to connect the battery for the first coil and for the battery for the second coil. And here it should have the same mutual inductance. It should have the same mutual inductance. Like this. Okay. So yeah, so this is pretty much about the mutual inductance. Okay, so here let's see a sample problem to see what it really means. So actually the experiment, the second experiment about the magnetic induction is quite similar to this setup and also related to this mutual inductance. Okay, so it says the figure shows two circular closed packed coils, the smaller radius R2. So this is smaller one, and then with N2 turns, radius R2 N2 turns, being coaxial with the larger radius R1 with N1 turns and in the same plane. So coaxial in Chinese is called 同轴. 同轴 means because it is a cylinder, this is another cylinder. So for a cylinder like this, Of course, for each circle, we have a center. For example, we have a center. And if you try to connect the center and then you try to extend, this is called the axis of the cylinder. So this is the 轴 of the cylinder. So which means that coaxial means this cylinder and that cylinder share the same axis, which means they are coaxial with a larger one, so radius r1 and n1 turn, and in the same plane. So derive an expression for the mutual inductance M for this arrangement of these two coils, assuming R1 is much larger than R2. So here the setup is that we have a battery connecting to the larger coil. Of course, if it is current, then it will generate B field in between. And then, of course, there will be magnetic flux going through the second coil. And so in that case, if the current is changing, then there will be induced current for the second coil, and then it can be sensed by this ammeter. So here, we try to derive the mutual inductance. Maybe it's a bit complicated. So here it says, so first of all, we try to phi 21, which is B1, A2. So why B1, A2's originally phi is only B times A. Here it means that we have current. We have current from the first coil. So the B field is actually generated by the first coil. So here we put B1. And then for the A2, rather than calculating the whole area for the coil 1, we will generate some induced EMF for the second coil. So we only count the cross-section area of the second coil. So we have A2 here. So B1 times A2. And so for the definition of the L, it is originally like L equals N phi B over I. So for the mutual inductance, we should slightly modify it. It will be something like N2. N2 is the number of turns for the second coil times phi 21. Phi 21 is actually this one over I1. Okay, so so which matches all the variable here. Okay, so it is nothing but N2 and then B1A2 over I1. So we just put this one into here only. So M is actually this expression. Okay, so in chapter 29, we have an equation 29, 26, like BC is mu 0 I R squared, and then over 2 times R squared plus C squared to the 3 over 2 power. So that time we try to derive the magnetic field generated by a coil, by the magnetic dipole, and finally we try to see when Z is much larger than R, then what it will be, something like that, and we try to simplify it. But here we don't apply that condition. Here we try to make Z to be 0, because in this question it said that these two coils are at the same plane, which means that the Z direction you can regard it as the direction pointing out of the page. So as much as they are on the same plane, here we have a Z equals 0. So we just substitute Z equals 0 here. So finally we will get B1 is something like N1 times B0, which is N1 times mu 0 I1, and over 2R1. So here we should have I1, R1, R1, and then C equal to 0. So finally it will be like this, because here we have R1 squared. We have R1 squared to the 3 over 2 power. So in the denominator we have R1 cubed. So when cancel with this R squared, it becomes R1 in the denominator, something like this. So here we can also put this one into there. So yeah, so here we have M equals N1 mu 0 I1 over 2R1, which is still this one. Sorry. Okay. Times N2A2 over I1. So we just try to put B1 into here. So for the other term, N2A2 over I1 is here, N2A2 over I1. And then this B1 is nothing but this one. So we just put this one into here. Okay, so then we can just make some simplification. So we have mu 0 N1, N2, A2 over 2R1. So we just reorder the terms. And actually we can cancel I1 and I1, so it does not relate it to the current. Yeah, so finally we also substitute A2 to be pi R2 squared. Yeah, because it's a cylinder, the cross-section area is a circle, so pi R2 squared. And then we also put this one into here. So finally, M is mu 0 N1, N2 pi R2 squared over 2R1, or we can just reordering something like pi mu 0 N1, N2 R2 squared over 2R1. So this is the closed form expression for this question. So yeah, looks a bit complicated, but yeah, you need to distinguish which one we should put 1, which one we should put 2. So here we try to generate some current for the first coil and generate the magnetic flux for the second coil. So yeah, so as much as you know what is going on, then you know which one to put 1, which one to put 2 for the subscript, and then finally you can actually get this expression. And then here we have a part B. But it only asks you that N1, N2 to be this number, R2 is what? This one, R1 is this one. What is the value of M? So which means that we just put all the number in this expression only. So which means that N equals pi mu 0, and then N1, N2, R2 square all over 2R1, and then we put in the number pi times mu 0 is 4 pi times 10 to negative 7, and then times 1200, and then square, and then times R2 is this one, 0.011, and then over 2, and then R1 is 15 centimeters, 0.15. So this is 2.29 millihenry, like this. Yeah. Okay, so before concluding this this chapter, we have 2 additional problems. So here it says a long coaxial cable consists of 2 thin wall concentric conducting cylinder with radii A and B. So here you can see this is A, this is B. So this is the inner one, this is the outer one. This is the outer one. And then the inner cylinder carries static current I, and outer cylinder provides the return path for that current. The current sets up a magnetic field between the two cylinders. Calculate the energy stored in the magnetic field for the length L of a cable. Okay, so here it so here we should try to calculate the energy stored in the magnetic field. But here what we don't know is that we don't have a uniform energy conservation because the B field is not uniform. So here we try to derive the B field first, because we keep in mind is that UB is something like 1/2 Li squared. 1/2 Li squared. But actually, we don't get the value. We don't know what is L yet. So here we should try to find UB. Small UB is small UB is 1/2 B squared over mu 0, and we can clearly know that B is not uniform. So let's try to find this one and then try to do some integration. Okay, so here we define the Ampere's loop. The Ampere's loop in the dotted line, and then we try to apply the Ampere's law. So we have a line integral of B dot ds, which is mu 0 I. So because we have I in the inner one, the direction is not really important here. We only need to know the value. So here we have a B times 2 pi r. So we suppose this one is r. This one is r. The radius of the Ampere's loop is r. Equals mu 0 I. So here we have B equals mu 0 I over 2 pi r. So which is the similar expression for the straight wire. Okay, so in that case, we can make use of this energy density stored in the magnetic field. So UB is 1/2 B squared over mu naught. So in that case, we have 1/2 mu naught, and then times mu 0 I over 2 pi r, and then quantity square. So it becomes 8 pi square, and then also I square. And then we have mu 0 square, cancel with this one, which is mu 0. And then we have I square. Okay, so DUB will be UB times dV. V is the volume. So this is nothing but mu 0 I square over 8 pi square r square, and then dV. And then so this is actually the cylindrical coordinate. So this dV is mu 0 I square over 8 pi square r square, and then this dV becomes r d theta dz. Okay, so for this part it is the same as the polar coordinate, and then dz is the axis perpendicular to it. So so this is not so difficult. So you just multiply this one by the one for the polar coordinate. Then this is for the volume for the cylindrical coordinate. Okay, so here we have UB, the overall UB, the capital UB. Capital UB is the integration of dUB. So it is like dUB. So it is like, so mu 0 I square over 8 pi square. are all constant to R, theta, and C. So nothing special. And then here we have R squared multiplied by R. So we only have dr over R only. And then we integrate from A to B. We integrate from A to B because A is the inner surface, B is the outer surface. So we only integrate from A to B rather than 0 to R. And then for the d theta, we only integrate from 0 to 2 pi because it is a whole circle. And then for dz, we integrate from 0 to L because L is the length of a cable. So finally, this one is lateral log of B over A. This one is 2 pi. This one is small l. So finally, the expression will be mu0 I squared and then times L over 4 pi and then natural log of B over A. Okay, so this is the expression for the energy stored in this structure. And what is the stored energy per unit length? So here we have L on the right side. So we just move this L over. So we should have UB over L is mu0 I squared and then over 4 pi times natural log of B over A. And then we just plug in this value and then it's done. So mu0 over 4 pi is 10 to the negative 7. Okay, and then times I squared is 2.7 square and then natural log of B over A. So both of them are millimeter square. So it is like 3.5 over 1.2. Of course, you can write times 10 to the minus third over 10 to the minus third and then they cancel. So finally, this is 7.8 times 10 to the negative 7 joule per meter. So this is the energy per unit length. Energy per unit length. So we have this as I unit. Okay, so before we end, we have the final additional example. So here it says the two parallel loops of Y have a common axis. So still, which means that if we have this center, and then we try to connect, this axis is perpendicular. It's perpendicular to this loop and also this loop. Then we call it have a common axis because this axis should be perpendicular to the plane. Okay, so the smaller loop radius out, the top one, is above the larger loop by the distance x. This x is much larger than capital R. So this is quite far away, but of course you cannot draw too far away. So yeah, so it just tells you here. So consequently, the magnetic field due to the counterclockwise current in the larger loop is nearly uniform throughout the smaller loop. Because as we have calculated in the previous chapter, we only know the B field generated in this z-axis rather than the point near. But as much as x is much longer than R, then we can approximate that the B field over this area is uniform. Of course, it is not, but the change might be small. The changes might be small. So we just approximate that the B field over this circle is uniform. We just assume that all the B field takes the same value as the center point. And then it will simplify the calculation. Okay, so yeah, so here it says, suppose that x is increasing, which means that this loop is moving up. Maybe this loop is not changing, so this x is increasing at a constant rate, v equals dx dt. And then find the expression of magnetic flux through the areas for small loop as a function of x. So in the previous chapter, we know the B field generated by this loop and this axis is this one. So, and of course, here we do not have z, we have this one is the x-axis. So rather than having c here, we change this z to x. So, which means that we have b equals mu 0 over 2 pi, and then times mu over x cube, and rather than writing it as mu is the magnetic dipole moment. Maybe some of you forget it during the midterm exam, but this is magnetic dipole moment, which is the number of turn times the I times the cross-section area. NIA, near, okay, near. Yeah, so here the number of turn is 1, so n is 1, so it is only I times the cross-section area. And here is a circle, so it's pi r squared. So this one is nothing but I times pi capital R squared. Capital R squared. Okay. Yeah, because it's generated by this one, so we put capital R rather than small r. But we assume that all the B field is approximately this value. Okay, so find B is approximately B times A, which is mu 0 over 2 pi times I pi capital R square over x cube times this A is pi small r square. Okay, so all in all, it is pi mu 0 I small r square capital R square over 2x cube. So this is the expression for the magnetic flux. Okay, for part A. And then for part B, it asks you the expression of the induced EMF. So according to the Faraday's law, we know that induced EMF is negative d phi b dt. So we can put this expression here. So we have a negative d dt, and then we have a pi mu 0 I small r square capital R square over 2x cube. Okay, so all the things are independent to the t. Say all these terms are independent to t. It doesn't change with time. And also these two. So the only thing change with t is x, because just mentioned that this loop is moving. This loop is moving upward. Okay, so finally we have negative pi mu 0 I R square and then capital R square over 2, and then we have a d dt and then 1 over x cube. So calculus time. So we have negative pi mu 0 I R square over 2. So this is 1 over x cube, which is x to the negative 3. So when we take the derivative d dt, it is actually negative 3 to the 1 over x to the 4th power. And don't forget the chain rule, so we also need to multiply by dx dt. So this is for the chain rule. Okay, so finally the expression will be like 3 pi mu 0 I R square capital R square v. So this dx dt is actually v. This is the velocity, not the voltage. Okay, over 2x to the 4th power. So this is the closed form expression. Okay, so for the C, it asks you the direction of the induced current. So for the induced current, because this one is moving up, and in that case, the B field is originally pointing up, because here I is counterclockwise. B field is pointing upward according to right hand rule. you use your forefinger, follow the direction of the current. Your thumb is pointing up. The B is pointing up. But as much as this loop is also moving upward, so this B is decreasing. As much as this B is decreasing, B induced should be pointing upward due to the Lenz's law. So in that case, according to right-hand rule also, the induced current should be counterclockwise. So the direction of the induced current is counterclockwise. Counterclockwise, like this. Okay. So yeah. So here we finish off this chapter, and I will see you on Thursday.